Uh, I think we can start. So welcome again to Geometry, Arithmetic, and Differential Equations of Period seminar. So today, Nils Matthes is going to talk about the Rham fundamental groups of punctured elliptic curves. So Nils, please go ahead.
Well, thank you very much. Thanks for the invitation to speak here. It's a pleasure. And yes, as Hossein said, I'll be speaking about Durham fundamental groups of punctured elliptic curves. And everything I'll speak about is joint work in progress with Tiago Fonseca, who's also at Oxford. Maybe before I begin, a word about questions. So I very much welcome questions during the talk. So if you have a question, just let me know. Just unmute your microphone and just ask. I will not be able to monitor the chat, unfortunately. So I think that would be easiest if you just ask your question like you normally would in a normal in-person talk. All right. So I would like to start with some motivation for this project with Tiago. And the motivation goes back to a very influential paper that many of you, if not all, will probably know. So Deligne, in 1989, in his paper on the fundamental group of P1 minus 3 points, defined the Rham fundamental group of the projective line minus 3 points, 0, 1, and infinity. And well, in fact, he not only introduced the Durham fundamental group of P1 minus 3 points, but he introduced something more general that's called the Motivic fundamental group of the projective line minus 3 points. And the Durham fundamental group is its Durham realization. So it's constructed in this formalism of motives due to Grothendieck.
I'm sorry, am I the only one who can't see your screen?
I'm seeing.
So the water, this is your problem. I think you have to pin down, I think, the screen.
Is there a problem with the screen? Can you see it, or?
No, it's okay.
No, I'm sorry. Now I can.
Okay, great.
Thank you.
All right. So not only did he define the Durham fundamental group of the projective line minus 3 points, but he studied and introduced a more general object, the Motivic fundamental group. And the Durham fundamental group is its Durham realization in the usual sense of motives. And I will tell you later on very precisely what the Durham fundamental group of P1 minus 3 points is. But since the seminar is supposed to be about periods, let me maybe say at this point, just for sake of motivation, what its periods are. So its periods are the multiple zeta values. So this is somehow implicit in Deligne's paper. It's later worked out in complete detail. So it's not going to be so important what multiple zeta values are for this talk, but let me just remind you of them, because the definition doesn't take long to write. So they're just these nested sums here. So these are real numbers, and k1 up to kd, those are positive integers, and k1 should be at least equal to 2. And what this Durham fundamental group does for you is it allows you to kind of study these multiple zeta values, which are just real numbers, allows you to study them geometrically. And a very important part of this geometric study was in fact only achieved much later by Deligne and Goncharov in 2005. So what they did is they made precise in which sense the Durham fundamental group is a motive. So they showed that that the Durham fundamental group is the Durham realization of a mixed tape motive. So the point here is And here by mixed tape motive, I mean in the sense of Vojevodsky. So the point here is that when Deligne wrote his paper in 1989, there was no good category of motives available at that time. But then subsequently, there was the very influential and very important work of Vojevodsky, which then kind of allowed Deligne and Goncharov to lift the construction of the motivic fundamental group to the category of mixed tape motives. And a consequence for this is for the study of these multiple zeta values, the consequence is that there's some kind of, I put this in inverted commas, there's a motivic Galois theory of multiple zeta values. So I'm not going to make this precise, but what you should think at first approximation is that inside this formalism of motives, you can construct an analog of the Galois group that's called the motivic Galois group. And the motivic Galois group is going to act on periods. It takes a bit of work to make this precise, and the way I say it is actually not exactly how it's working. But you can think about it that you get a group action on multiple zeta values in a way that preserves all the algebraic relations. And like classical Galois theory is very, very useful in the study of algebraic numbers, so is the action of this motivic Galois group for multiple zeta values. And very importantly, Francis Brown, in 2012, he studied this motivic Galois action in great detail. And what he was able to show is that, so he proved that the Durham fundamental group of P1 minus 3 points in fact generates the category of mixed tape motives.
Do you mean the motivic fundamental group?
Yeah, well, I mean, you will know this, but the Durham fundamental group, I mean, you can view a motive as the Durham realization together with the action of the motivic Galois group. So that's what I mean here.
Okay.
Yeah, you're right, of course. So of mixed tape motives, and actually mixed tape motives over the integers, to be technically precise. And so again, his proof is kind of Galois theoretic in nature. So his proof proceeds by studying Galois theory of multiple zeta values, and it has applications. Let me just mention that this also has applications to the structure of multiple zeta values. So there's some conjectures on multiple zeta values that Brown was able to prove. More precisely, the so-called Hoffman conjecture, which gives you a generating set for multiple zeta values. So, and some of the motivation for this project with Tiago is that you want to somehow do something similar. Do something similar for elliptic curves. So instead of the projective line minus 3 points. More precisely for once-punctured elliptic curves. But this is, I mean, this is not so easy. It's actually quite difficult, particularly because of some complications having to do with motives. So what the goal for today is more modest. The goal for today is to make this very first step in the story that I just told you for elliptic curves. So today is just going to be define the Durham fundamental group of once-punctured elliptic curves. So I will not mention motives at all. And I'm afraid there also will be no periods really appearing. But maybe I come back to this at the end. All right, so that was the introduction. So now let me, as I promised, I should tell you something about the Durham fundamental group of the projective line minus 3 points to get us started. I should tell you what it is. And what this is supposed to be is somehow, it's supposed to be a version of the fundamental group, which is constructed purely in the framework of algebraic geometry, meaning that everything should be completely algebraic, and you don't want to use any, say, topological constructions, which somehow involve, say, the field of complex numbers with its topology. You don't want to do this, but nevertheless, kind of the definition is very much inspired by the classical theory of the fundamental group. So let me start with an analogy, with the analogous story for fundamental groups of topological spaces. So let's say T is a topological space. And I need to assume that it is both connected and locally path connected. And I also fix a point T, little t, big T, which is going to play the role of the base point. Then how do you define the fundamental group in this setting? Well, that's very well known. So how do you define it? So the fundamental group of the space T with base point T is defined as the set of all paths, so continuous maps from the unit interval into your space T, which start and end at the point T. And you mod out by an equivalence relation that is called homotopy. So somehow you want to identify two paths if they can be deformed continuously, one into the other. But the problem is, I guess, if you want to do something similar in algebraic geometry, then the problem is somehow that the topological spaces you encounter in algebraic geometry naturally, they're not really nice from a topological point of view. And the notion of path is not such a good notion. I mean, you could of course naively define paths on an algebraic variety, but this is not the right thing to do. Instead, what we are going to do is we're going to use a slightly different interpretation of the fundamental group, which is also well known, namely an interpretation of the fundamental group in terms of covers. So this works as follows. So if you have your topological space T, what you can do is you can look at the category of covers, or, well, I'll actually use the equivalent formalism of locally constant sheaves on T. So just sheaves of sets which are locally constant in the sense that for any point there's a small neighborhood such that the restriction of the sheaf to that neighborhood is constant. And if you're given such a locally constant sheaf, you can associate to it its fiber. So let's say this just goes into sets. If you have F, then you can associate to it its fiber at the point T. And let's call this functor omega T. And the point is that now on this fiber here, you have an action of the fundamental group. There's a left action of the fundamental group on the fiber. So, and again, if you think in terms of covers, this is just means if you look at the fiber over any point of your cover, there's going to be an action of the fundamental group which permutes the elements of the fiber. And what you can show is that this gives an equivalence of categories between locally constant sheaves.
I'm sorry, those are sheaves of sets, no?
Of sets, just of sets, yes.
Okay.
Locally constant sheaves on T with the category of left pi1 sets. So yeah, so these are just sets. So there's no topology or whatsoever involved. On the right hand side, it's just sets together with an action of the fundamental group. And in fact, you can reconstruct the fundamental group. So if you remember this functor omega t, you can reconstruct the fundamental group. Namely, the fundamental group is just the automorphism group of this fiber functor. So here, automorphism in the sense of category theory, so natural transformations, which are isomorphisms. And the point is that, so whereas the point of view on the fundamental group using paths does not really have a good analog in algebraic geometry immediately, what does have a good analog in algebraic geometry is this notion of locally constant sheaf. So the analog in algebraic geometry is the following. So let's first introduce the analog of the topological space. So we have K, so field of characteristic 0. And we'll be looking at a smooth and geometrically connected variety. And then the analog of a locally constant sheaf is the notion of a vector bundle with connection. So we're going to look at pairs V, nabla, where V is a vector bundle on X, and nabla is an integrable connection. So let's write this out. So it's just a morphism of sheaves like this. And it's integrable, which means that its curvature is 0. Okay, so this is in some sense an analog of a locally constant sheaf in algebraic geometry. But for technical reasons, we're actually going to restrict our attention to only a subclass of these. So we're going to restrict to so-called unipotent vector bundles with connection. So what does this mean? So unipotent means, well, intuitively, it kind of means that your vector bundle is built out of trivial bundles via successive extensions. So you should think of this as a class of particularly simple vector bundles. And the formal definition is the exists of filtration by subbundles. So these are subbundles. They're stabilized by the connection. And what you want to happen is you want that the successive quotients are isomorphic to a trivial bundle for some Ri, for some integers Ri. And we'll denote by UVic for unipotent vector bundle with integrable connection, the category of those. All right, so, and this is going to be our analog of the category of locally constant sheaves on a topological space. So how do we get from there the Durham fundamental group? Well, now, given any base point, which is going to be a k-rational point of big X, what you get is you get a fiber functor omega X very similar to before, except now it takes values in the category of k vector spaces. And it's called a fiber functor because what it does is it takes the vector bundle with connection and maps it to the fiber at X of the underlying bundle. So you can also think of this as the pullback of the vector bundle along the point X. All right, and well, now at this point, I can already give you Deligne's definition of the Durham fundamental group. And what you do is you define the Durham fundamental group pi1 Durham to be the automorphism group of this fiber functor. And in fact, you only take automorphisms which commute with the tensor product. So these are the automorphisms. Of omega X that, respect the tensor product. So this is a group in the sense of algebraic geometry. So more precisely, this is a pro-affine algebraic group. Over K. So this just means that it's a projective limit of matrix groups. And that's the Durham fundamental group.
Nils, I have a question. If
yes.
Is the field of complex numbers, so do we have this comparison theorem that this is just classical fundamental group? Because you restrict it to a very special class of extent shifts.
Right, exactly. So if you work over the complex numbers, what you're getting is not exactly the fundamental group. You get a so-called Maltsev or pro-unipotent completion.
So it is different.
So
okay.
It is different. Yeah. So, but that's actually a very good point. I mean, you could, of course, it's a very natural question to ask, why am I restricting, or why did Deligne restrict to unipotent vector bundles with connection? So if you're interested in periods, what normally happens is your variety is not defined over the complex numbers, but it's defined over a smaller field. Usually it's a number field or something like that, or the rational numbers. And the problem with, if you work with general vector bundles with connection, then what you want to do is, as you said, you want to go to the complex numbers, and then you get some kind of comparison isomorphism with the classical fundamental group. And you want to define a rational structure on the fundamental group coming from the Durham fundamental group. But the problem is that with the general notion of vector bundle, this does not work, because the formalism of the fundamental group with general vector bundles does not commute with base change. So the point here is with this here, with this definition, this commutes with base change. Or let's say just with the extension of scalars. That's actually enough for our purposes. And the general version does not, unfortunately. For this, really, unipotency is crucial. So.
Walter, your mic, please.
and can't be, sorry?
That's okay.
Oh, okay. Right, so the unipotency assumption is crucial for this to work, which is why we restrict to these bundles. All right, great. So what I just described for you works for any smooth geometrically connected variety. So, but now let's specialize to the projective line minus 3 points, because there's something very interesting happening here, in fact, regarding these fiber functors. So what happens here is, as observed by Deligne, there exists a canonical fiber functor. So canonical meaning here, it does not depend on the choice of, you don't need to fix a base point for it. So there's a canonical fiber functor here. And how is it defined? Maybe here, case actually Q. So how is it defined? So you take your vector bundle with connection, and actually you can extend this vector bundle with connection to a vector bundle with connection on the projective line, and the connection has at most logarithmic singularities along the divisor at given by 0, 1, and infinity. So that's called the canonical extension. And what you do now is you take this vector bundle, this extended vector bundle, and you take its global sections. And of course, you could do this in general. I mean, for any variety. But the point is, this is really a fiber functor. The reason why this is a fiber functor because of the following properties. So the sheaf cohomology groups of P1 with coefficients in the structure sheaf are particularly simple here. So the global sections are just Q, so the only functions are constant. And the H1, in fact, vanishes. And this was observed, it was observed by Deligne that whenever you have these conditions given like this, then you can play a similar game and you get a similar canonical fiber functor. So these are sometimes were afterwards known as Deligne's good conditions. Right. And let me record the consequence of the existence of this canonical fiber functor. So there are two consequences. First of all, this fiber functor, in a sense, you can view it as universal among these other fiber functors, in the sense that every fiber functor for a base point x comes from this canonical fiber functor. And the first consequences because of that is that actually pi1 Durham of the projective line minus 3 points is independent of the base point. And again, if you think about the analogy with topology, so in topology, you also have, you can also look at the fundamental groups for different points. And whenever you choose a path between these 2 points, you get an isomorphism of the corresponding fundamental groups just by conjugation. So and what this kind of tells you is that there is a canonical.
I'm sorry, does it mean that for any fiber functor, the automorphism group of all of them are isomorphic?
Yes, exactly.
Okay.
Exactly. Canonically isomorphic. I mean, they are always isomorphic, but not canonical. So the point is that if in the analogy with topology, you can say that there's a canonical, we put this slightly in inverted commas, can be made precise, but there's just a canonical Durham path between any 2 points x and y. Let's say that x and y are Q-rational here. So yeah, exactly. So there's somehow a way to canonically compare these two fundamental groups for any choice of base point. Yes?
I didn't understand this, the relation between this Deligne's extension V bar and then the Deligne's good conditions.
That's two different things. So the canonical extension you can always do. It works, I think, in great generality. That's nothing particular to P1 minus 3 points. But these Deligne's good conditions are very particular to the projective line.
Okay.
I mean, in some sense, what this tells you is that every vector bundle on P1 minus 3 points has a canonical trivialization, in the sense that there's a canonical way to trivialize any vector bundle on P1 minus 3 points. Yeah, and I mean, Deligne himself didn't call it his good conditions, obviously, but somehow it's, and some people like to call it that way. Any more questions?
These good conditions, do they imply the existence of this canonical fiber functor or something like that?
They imply that this here is a fiber functor. So because a fiber functor, in a technical sense, is a functor which is both exact and faithful. And if you just stare at the definitions, then this here tells you that it's exact. And this here tells you that it's faithful, basically.
Thank you.
And it also follows that it's compatible with tensor product somehow. So that's also not immediate, but follows from these conditions. All right, and another consequence you can draw is that you can also compute the Durham fundamental group from this observation. So more precisely, you can lift this canonical fiber functor to an equivalence of categories between the category Uvic and well, it's going to be a category of vector spaces together with some extra structure. And more precisely, this is going to be the category of right comodules for a certain kind of coalgebra, namely the tensor coalgebra on H1 Durham of X. So the algebraic Durham cohomology of X. So somehow this is telling you that a connection on a unipotent vector bundle is encoded by a comodule structure for this coalgebra here. So if you want this slightly more explicitly, this is just, as a vector space, this is just the direct sum over all tensor powers of H1 Durham of X. Okay? And by Tannakian duality, this result implies that the Durham fundamental group, I'm going to omit the base point because it doesn't depend on it, is isomorphic to the spectrum of this tensor coalgebra. So you're getting a very explicit description of the Durham fundamental group in that way. And let me just add orally that this explicit description of the Durham fundamental group is absolutely central, for example, in Brown's work on mixed tape motives and multiple zeta values. So you're really crucially exploiting the fact that somehow this Durham fundamental group is very explicit. And also the Galway action on it, defined via the formalism of motives, can be made very, very explicit on this Durham fundamental group. Okay, I think that's all I want to say about the Durham fundamental group of P1 minus 3 points. So maybe let me ask you if there are any questions at this point, and if not, then I'll go on to the elliptic curve situation. Okay, so
maybe just
yes.
So far, why it is just 3 points removed? It's not issue. I mean,
Sorry.
You started from P1 minus 3 points.
Yeah. Yes.
But
you can remove more points. You can remove any finite number of points that you want. That's no problem. Is that what you mean?
Yeah.
Yeah, you can. Exactly. You can. A similar result holds for a P1 with any number of points removed, or more generally, a similar result also holds whenever you have a smooth geometrically connected variety which admits a compactification satisfying Deligne's good conditions. Then you get a similar kind of result. But the problem is that Deligne's good conditions are pretty restrictive. So for example, for curves, it's actually equivalent to its compactification being P1 minus 3 point, P1 minus. Right. Okay, so, and I guess I already jumped ahead a little bit when I mentioned this. So now kind of the goal is to do a similar thing for an elliptic curve. So I want to define a Durham fundamental group. For an elliptic curve, more precisely for a once-punctured elliptic curve. So what is my setup? So the setup is going to be, I'll work in a relative situation. So S is going to be a smooth, geometrically connected K variety. K is always a field of characteristic 0. And I'm also going to impose another technical condition. Namely, we want that its dimension is at most equal to 1. So it could either be a point, spec K, or it could be a curve. For much of what I say, this will not be important, but for the main result to hold, this will be important. And then F from E to S is going to be an elliptic curve. And inside of it, we have the open subscheme, which is obtained by removing from E the 0 section. So that's our once-punctured elliptic curve. So for example, something which a good example to have in mind is you could take the universal elliptic curve where S is, say, the modular curve Yn of full level n, at least 3. So Y of n is a curve and satisfies all these conditions above, so we allow it. So, and the first thing that we have to do is we have to settle the question of what is the analog of this unipotency condition. So this is something completely general, has nothing to do with elliptic curves, could be defined much more generally. So say a vector bundle with connection nabla is relatively unipotent. If there exists a filtration similar to before by subbundles which also should be stable under the connection, such that the successive quotients now are not trivial, but rather relatively trivial, meaning that it comes via pullback from S. So Wi here is some vector bundle. Over S. And you can check easily that this is really a generalization of the previous notion of unipotent. In the case where S is spec K, a vector bundle is just a vector space, finite dimensional vector space, and you get the trivial OX modules via pullback. So this really just generalizes the notion we had before. And we'll denote by UVic E prime over S. That's the category of such pairs. Okay. And again, we're just going to try to copy everything that we said before in the case of P1 minus 3 points. So whenever we have a section, so whenever we have a point, we get a fiber functor. Which now takes values in the category of vector bundles over S and is defined as before. You take your vector bundle and you pull it back along E. So that's again a fiber functor. And that's great. And you could consider the automorphism, the automorphisms of this fiber functor to define a relative version of the Durham fundamental group of the once-punctured elliptic curve. But the obstacle now is, compared with the P1 minus 3 point story, is that the elliptic curve E over S does not satisfy Deligne's good conditions. Because for curves, Deligne's good conditions, one of Deligne's good conditions is that the curve have genus 0. And well, an elliptic curve just does not have genus 0. So more precisely, the problem is that the relative first cohomology does not vanish. It's equal to OS. Okay. And another way of putting it is that not every unipotent vector bundle on an elliptic curve is trivial. However, in a way, that you can trivialize all these vector bundles all at once and hence get around this problem. So this was also suggested by Deligne. You can get around this problem by replacing the elliptic curve E over S by the universal vector extension of E. So what is the universal vector extension? And just to give you an idea, so I'm not going to define it precisely, but the universal vector extension sits in a short exact sequence like this. Where this guy here on the left is a vector group. So in particular, E natural is an affine bundle over E. And if you think about it topologically again, I mean, an affine bundle should of course be, just a bundle with fiber and affine space. Then the point of this is that somehow the Rham fundamental group of the elliptic curve and of its universal vector extension are the same. So more precisely, the pullback functor from unipotent vector bundles on E over S to unipotent vector bundles on E natural over S with connection is an equivalence. Right, so again, this is, if you think about it topologically, this is kind of clear, because if you have an affine bundle, then its fiber has a vanishing fundamental group, and you can show that the fundamental group of the affine bundle is the same as that of the base space. And something similar is happening here. But the gain is, well, actually, the universal vector extension, I'll denote the structure map by F natural, satisfies Deligne's good conditions. So in fact, it satisfies the relative analogs of Deligne's good conditions. And this implies in turn that you can again define a canonical fiber functor on the universal vector extension in exactly the same way as before. So what is it? You have your unipotent vector bundle with integrable connection. So what do? You first extend the vector bundle, which is defined over the punctured elliptic curve. You can extend it to the whole elliptic curve. Then you pull it back to the universal vector extension, and then you take global sections. And again, the fact that this is a fiber functor really crucially relies on these conditions. All right, and now let me state the theorem. Which is going to be the analog of Deligne's computation of the Durham fundamental group of P1 minus 3 points. So this canonical fiber functor can be lifted to an equivalence of categories as follows. Again, the connection part is going to be encoded by a co-algebra, by a co-module structure. So it's going to be right co-modules for, so this is going to be a bit of a mouthful, so it's going to be, I'll just write it out before I tell you what it is. So so D is the pre-image of the zero section. So remember, pi was the projection from the UVE to the elliptic curve. So, and this here, So this here is maybe that, but okay. So this here is the bar construction on this guy here in the middle. So yeah, it's the bar construction. So right. So let me make a few remarks, which will, I mean, hopefully get you a slightly better feeling about this guy on the right. So let's, to avoid writing it over and over again, I'll call this A, Durham, E prime of S. So the first remark is that, well, this seems a bit unwieldy, but in fact is you can compute this completely explicitly. Can be computed completely explicitly in terms of differential forms on the UVE. With log poles along the divisor D. And over the complex numbers, so if K is the complex numbers, then you can write these down in terms of theta functions. Kronecker theta functions, to be precise. So you can make everything completely explicit and you can compute with it and whatnot. It also relates to cohomology. So there exists an increasing filtration, W for weight. And its associated graded pieces can be identified with Durham cohomology. So if you take the associated graded pieces for this filtration, you get the tensor coalgebra on H1 Durham of the punctured elliptic curve. So this is kind of similar if you remember Deligne's result. So in Deligne's result, kind of the filtration is canonically split already, and you get this result in terms of the tensor coalgebra on Durham cohomology. Here it does not split, but nevertheless, there's a similar result at the end. So, and for this reason, you can kind of think of a Durham of E prime over S as a kind of non-abelian Durham cohomology. So this term has different precise interpretations. I'm not claiming this to have a completely precise meaning, but you see, I mean, somehow the point is that it's kind of a generalization of Durham cohomology.
One question.
Yes?
The condition that you put, this Deligne's condition is for E, and then you used in the main statement E prime, the punctured one. And it is, it's like this, no? I mean,
right. Well, yeah, exactly. I mean, the point is somehow that you know the elliptic curve and its universal vector extension have the same kind of Durham fundamental group, and also the once punctured elliptic curve and the there's a way to relate the Durham fundamental groups of the once punctured elliptic curve with the complete elliptic curve. So.
Okay.
Does that answer the question? Okay. And the final remark that I would like to make is that there's also an integrable connection on this guy. And again, if you take if you look at the associated graded for this connection, then this is the Gauss-Manin connection. On, well, this tensor coalgebra upstairs here, so let's just say on H1 Durham of E prime of S and on every tensor power. So again, if you want, you can think of it as kind of a non-abelian Gauss-Manin connection. So it's generalization of this to this more general setting. Okay, and yeah, there would be more things to say here, I guess. So of course, we're particularly interested in the study of periods, and yeah, you can try to compute the periods and see what you get. And using this result that I mentioned above here with the Kronecker theta function, you can actually also compute its periods. And yeah, and then there would be, of course, 1,000 more things to do. And but maybe I should stop here. And thank you very much.
Okay, thank you very much, Nils. Any question? Okay. Any question before I ask my question? Okay, so let's record my question. So if I didn't know about all this stuff, and I wanted to really construct this the Rham homotopy group, I would start by this notion of iterated integrals, for example, because
right.
But so far I didn't because like in the case of iterated integral, I have the duality also, the Durham duality between the classical homotopy and I mean, do you plan to connect it to this change iterated integral, this stuff, or?
Yes, absolutely. So I haven't really spoken about this at all, but you can view this space here if you want. So that space here. So this is a space of iterated integrals, algebraic iterated integrals. So you know Chen's theory. I mean, if you're familiar with Chen's theory, then you will probably have seen a similar type of construction involving the bar construction. But what Chen is doing, he's working with smooth differential forms. I mean, he's working on the smooth manifold, and then you're working with smooth differential forms, and then things are, of course, a little bit simpler because, I mean, you have honest complexes computing your Durham cohomology group. Whereas if you do things algebraically, then you always have to choose resolutions and so on, unless you're in special cases. But yeah, I mean, if you want, then this is precisely an algebraic incarnation of what Chen has done in a special case. Yeah, absolutely.
Okay.
And you have in particular, you have a kind of period map. If you want, you can really, if you work over the complex numbers, you can integrate your iterated integrals and get some interesting numbers.
Okay, maybe just so that the people feel better asking questions, I stop recording. Just a moment.